So a sequence is just a function, and it's a particular way of writing the images themselves. And so if we have simply, say, n equals whatever, say 0, 1, 2, the sequence itself is normally written as this particular rule. This here is a function where n is going to map to things, and then we usually just write it a0, a1, a2, a3, etc. And so we need to be able to go back and forth between the two. Here's a rule, here's the numbers, here's the numbers, here's a rule. It's a creative process. A sum is simply we take parts of this sequence and just simply add them up. An example, we could do the sum, say from I equal to 3 to 7 of 2 plus 3i. That rule is what type of sequence? 2 plus 3i is what? It's called a certain sequence. It's arithmetic, right? It's an arithmetic sequence. If it was 2 times 3 to the I power, that would be geometric, right? So there's certain ones we need to know. Definitely know the arithmetic, definitely know geometric, know ends, the squares, the cubes, factorials, at least several of the terms to be able to recognize them. All it says is we just plug them in. If I plug 3 in, what's the first value of the sequence? 11. If I plug a 4 in, what's the next value of the sequence? And then the next will be 17, and the next will be 20. And then so this was n equal to 3 became 11. N equal to 4 became 14. N equal to 5 became 17. N equal to 6 became 20. N equal to 7 became 23. Right? So that's all you have to do. That's the sequence. And a series is just add them up. And everybody can do basic arithmetic. Now, there's certain things, I hope. Actually, that's a bad thing because it's not true. We don't do enough arithmetic to get comfortable with series and sequences enough. Now, if we have certain ones, like if I have 1 plus 2 plus 3 plus everything up to 100, this is somewhat famous. There was I think it was 1 to 100. There was a teacher that was proposed to his class to sit there and keep them busy as they were learning arithmetic. It simply said, add the numbers from 1 to 100. So the kids are all grinding out like on this, and they're going to try to get the numbers from 1 to 100. And one of his students, who was rather young at the time, took a little bit, came up, handed him the answer immediately. And which was kind of and he was a good one. It's like instead of sitting there. Some teachers, when they see a student come up with a solution that's correct in a way that they didn't expect, will get angry. It's like, that's not how I wanted you to do it, type of things. A better approach is, I wonder why this is actually right. What the student had done was simply recognize that adding 1 to 100 is the same thing as adding 100 down to 1. And if you would do this, this would be just simply 101, and then another 101, and then another 101, and then another 101. And how many 101s are there? Forget his parrot. There's 1, 2, 3. There's 100 101s. And so this thing is just simply, that's 100 101s. So the sum itself, since that was the addition done twice, it has to be 100 times 101 divided by 2, which is 50 times 101, which is rather straightforward. What's 50 times 100? 5,000. 50 times 1, 50. So it is 5,050. Done. How would you like to have done 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus... Now those group of numbers, it actually forms what's called the triangular numbers, if you want to look at it like that. This sum itself, looking at it this way, if I would do, 1, and then I would add a 2, and then I would add a 3, and then I would add a 4, and then I would add of 5. So this is 1 plus 2 plus 3 plus 4 plus 5. Can you see why this particular sum is called the triangular numbers? Everybody nod your head and say yes. One of the why is that the triangular numbers is simply 1/2 of the last number times the next number. Well, if I had this triangular number here and I repeated it just below 1, 2, 3, 4, 5. That's a rectangle. What's the area of this rectangle? It's simply 5 times 6. And so what would be the area of the triangular number? It's the same formula, right? This is a geometric proof of the same formula. Why is it n times n plus 1 over 2? Because of this rectangle. Now, at the time when geometric solutions came into place, there wasn't such a thing as variables. They would say things like the sum from 1 to 5 is, and they would just simply say, this answer. And they would do a nice picture and say the sum of 1 to 5 is 5 times 6 over 2. Why? And they would just draw a picture. Because everything that existed had to physically exist. You had to show this because it represents a thing that you can physically hold or visually understand. So this would be a geometric proof of 1 to n. And so these are one of the things that we need to understand. That a sum that everybody should know would be what would happen if I added up from 1 to n of the I, that 1 plus 2 plus everything up to n. That's equal to n times n plus 1 over 2. There's a geometric interpretation of it. There is an algebra interpretation of it. The child who did this variant was Gauss. And I'd say most people would consider him to be, possibly the greatest mathematician of all time. And it's also a really good example of, in terms of Gauss himself, as the importance of having appropriate copyrights. In other words, actually having them limited in nature, and also recognizing why that's important. Because he was the son of a laborer bricklayer who, at the time, you'd like your kid to do what you do. But they started off education, but education could start in that era because there was such a thing as cheap paper and the ability to print on it easily. And Germany copyrights at the time was just print. It's like, but that was my book, I'll print it. And other people would print it, and so books were just, and knowledge spread like crazy. And so you had low-cost books. Like, for example, would you get rid of your book if this book was just $7? Would you probably keep all of your math books if they were like $5 to $7 each? That's about what it costs paper-wise, right? And the people would make money on it. Now, what would happen if you had all these books and students kept it and read that information and thought about it and had a thing to go back to? Do you think education would be going a little bit faster than it currently is? And the answer is yes, but that's what Gauss experienced. It's one of the reasons why German mathematics at the time surpassed the rest of the world, was because they didn't recognize copyright. People still made money, but knowledge was just spread so much more. It's kind of interesting, history of math there. All right. How could we do other things? For example, if this is one that we need to know, if you've had, since calc is a prereq for this course, you should start to recognize these, right? What would be the sum from I equal 1 to n of I squared, which is 1 squared plus 2 squared plus 3 squared plus 4 squared plus everything up to n squared. Now, one of the ways that we could do this to try and find a formula for it is, one of the bigger issues is the ellipsis. I don't know what's there. How high do I go? I don't know. I'd like to get rid of this particular ellipsis in a particular way. And one of the ways that we could do that is to introduce a new type of series called a telescoping series. And a telescoping series is this. It's the sum, say, from I equal 1 to n of a sub I plus 1 minus a sub I. Now a sub I plus 1 is a later term and a sub I is an earlier term. If I plug in I equal 1, this would be a2, and I'm going to subtract a1. That would be I equal 1 becomes those two things. Plus, plug in I equal to 2, and what would you get? A3 minus A2. If I would plug in I equal to 3, what would I get? It would be A4 minus A3. Now, the reason why this is called a telescoping sum, how many of you have seen like the old pirate telescopes, right? They open up and then they collapse. And it's like, oh, I need to see far. You can open it up. All right, for addition, it's associative and commutative, right? So are these parentheses really needed? No. So what's going to happen to my A2s? They will cancel. A1 doesn't have another A1, so he stays. What happens to my A3? It cancels. What do I notice canceling? What I notice canceling is if I have two terms beside each other, the left of the first term and the right of the second term cancel. Is everybody okay with that? Now, what would be the last two terms of this sum? This would be I equal n, and this would be I equal n minus 1, right? At I equal to n, this is a sub n plus 1 minus a sub n. What's this one? So a sub n minus 1. And what will I notice? Well, here's the deal. For my last two terms, who cancels? The left and the right cancel. Now, does this term have something inside the ellipsis? Of course. So A4 has something that it's going to cancel with. Does this guy's here right? Does an minus 1 negative have somebody inside the ellipsis to cancel? Yes, he cancels. So this entire thing has simply done what? Collapsed, like a telescope. And so what's left? That's become a sub n plus 1 minus a1. Where's my ellipsis? It's all gone, right? It's a nice series where if I just simply plug numbers in, and I don't try to calculate the numbers, I just write the entire thing out, I notice that things subtract. Now, if this number and this number are 1 apart, everything will subtract except for 1 on the beginning and 1 on the end. If they're 2 apart, like let's say that this was like an I plus 2 and an I. Those are 2 apart. So how many would be left at the beginning? 2. How many would be left at the end? 2. Well, what else will happen? Subtract. All right. How can that help me with my one problem? Well, let's consider this. Let's do a little bit of algebra. What would, say, I plus 1 squared minus I squared? If I did some algebra, what does that equal to? That's I squared plus 2I plus 1 minus I squared, which is 2I plus 1. So what do I know? I know that an I plus 1 squared minus I squared is simply 2I plus 1. What would happen if I had an I plus 1 cubed minus I cubed? Right, what's I plus 1 cubed? I cubed plus 3I squared plus 3I plus 1 minus I cubed, which is equal to 3I squared plus 3I plus 1. And so this is equal to I plus 1 cubed minus I cubed is equal to 3I squared plus 3I plus 1. Would the same thing happen if I did an I plus 1 to the 4th minus I to the 4th? Like, yeah, these are all pretty, straightforward. It's like, well, why am I interested in these sorts of algebra objects? Well, let's look at this guy here. Let's look at him for a second. Those must be equal. That would tell me that the sum from I equal 1 to n of I plus 1 cubed minus I cubed must be equal to the sum from I equal 1 to n of 3i squared plus 3i plus 1. Add the left for I equal 1, I equal 2, I equal 3, up to I equal n. Add the right, should get the same thing, right? Now, that is a what? Telescoping series. How far apart are they? 1. So everything's going to collapse except for 1 at the end and 1 at the beginning. So what's 1 at the end? n plus 1 cubed. What's the 1 at the beginning? Minus 1 cubed. Because this is simply telescoping. Ran out of space. But that's going to be equal to 3 times the sum from I equal 1 to n of I squared plus 3 times the sum from I equal 1 to n of I plus the sum from I equal 1 to n of 1. This is a formula. What's that guy right there? N times n plus 1 over 2. What's 1 plus 1 plus 1 plus 1 plus 1 n times? What is the only thing that I don't have known? That, the sum of the square. Could I solve for it? Yes. If we would do some algebra, we would find that the sum from I equal 1 to n of I squared would simplify down to n times n plus 1 times 2n plus 1 all over 6. There's actually a geometric proof for this one as well. Which is kind of interesting. You could look it up. Look for geometric proof online for the sum of I squared. But we can do algebra. Well, now that I know I squared, could I go and use this telescoping approach to find I cubed? Yeah, we would do I plus 1 minus I using the fourth power, simplify it. We would have an I cubed, an I squared, an I, and a constant. We know everything except for the I cubed. Go through the entire problem, do it all again. On the other hand, I cubed is a much easier one geometrically. Algebra, right? I'm just saying algebra. That's not pretty. This algebra is not easy. I mean, it's easy algebra. It's college algebra. It doesn't do too much, but it's not that nice. On the other hand, the sum from I equal 1 to n of I cubed, 1 cubed plus 2 cubed plus 3 cubed plus everything up to n cubed. Instead of writing it the way the book writes it, it's nicer to write it this way, which is n times n plus 1 all over 2, the quantity squared. If you write it that way, the geometric proof kind of jumps out a little bit. And so that would mean that is a square. That means my shape must be a what? A square. What's inside that square? What's the length of the side? N times n plus 1 over 2. Does that look familiar? That's 1 plus 2 plus 3 plus 4 plus everything up to n, right? So if I, for example, would do 1 squared plus 2 squared plus 3 squared plus 4 squared is going to be 4 times 5 all over 2, the quantity squared, right? Because, and what is this? This is 1 plus 2 plus 3 plus 4, right? It's a triangular number. Physically, what does this thing look like? I just make a square like this. It's not quite squarish looking. It looks better. I'll erase that part. So I make a square. And then I just make, here's a 1. And then I make a 2. And then I make a 3. And then I make a 4. I'm going to make a 1. I'm going to go up 2. I know these lengths aren't appropriate. All right, now let's connect this thing into L-shaped pieces. Now what happened is there was an old text. They didn't have algebra, they didn't have arithmetic, they didn't have this sort of symbology. What it said, and I think it was up to like maybe 6, but let's say, or 5 or 6, and it said the sum for this problem, it would say the sum of the first 4 square numbers is the square of the 4th triangular number. Because 1 plus 2 plus 3 plus 4 is the 4th triangular number. So the sums of, sorry, that's not squares, that's cubes. The sum of the first 4 cubes, right? 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed is the square of the 4th triangular. And they said, they drew a picture. They said, that's the proof. And then they stopped. People looked at, how in the world is that a proof? Well, you know what's kind of interesting is if you would go to this problem and say this L-shaped region is 2 trapezoids. If you calculate the area of this L-shaped region, it's going to be 4 cubed. If you calculate the area of this L-shaped region, it's going to be 3 cubed. If you calculate the area of this L-shaped region, it's 2 cubed. And what's that? It's 1, but that's actually also 1 cubed. So it ends up being that the areas themselves are cubics. The fun part is, how would you show that? And it's not too hard, because what is 1, 2, 4, 3, 4? That's a triangular number, right? So that means this side here is a triangular number, and this side here is also a triangular number. What's every square? Say a 3 by 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. If I would break it like this, is what? Every square is the sum of 2 neighboring triangular numbers. And they knew that. So if I would take this thing here and cut it, if I cut right here, took it and laid it up above, it's just a big giant rectangle. And what's the rectangle? Well, that would be ended up being, this would be a triangular number, and the sum, it would be the sum of 2 triangular numbers. It would be 1 to 4 and 1 to 3, which is a square. Which tells us that if I would cut it and turn it up, that's a square times 4. So it's 4 squared is a long length times 4, that's 4 cubed. And so they understood geometric numbers. It's the sum of triangulars forms a square times its side is a cube. What was interesting is they didn't have any explanation. They just simply drew the picture and said that proved it, which would assume that the readers were smart enough to figure it out. But readers would read that and look at it for a while and ask, how in the world did they understand that? Because they didn't have algebra. They had to have understood it as a concept of every one of these lengths is a triangular. So, all right, so that's the sums of the cubes. Another one that we need to know, say from 0 to n of AR to the K. The sum of a geometric series. All right, I just can't flip it and add it like Gauss did. But what I could do is to say, again, I would like to get rid of my ellipsis somehow. So if I would look at this particular sum, let's just simply call it S. What would, if S is this A plus AR squared plus everything up to AR to the n, what would be a S times R? Every one of these terms gets what? They'd all get an R. Right? Everybody gets an extra R. Now, what would happen if I said this S times R and take away S? Well, if I subtracted these two rows where that's a minus and this is a plus, what would happen to my ARs? They would cancel. What would happen to my AR squareds? They would cancel. Would AR cubed have an AR cubed here in the ellipsis? Yes. What happened to the AR to the n with an AR to the n? They would cancel. So everything would cancel except for, well, what happens? It telescopes. By subtracting those two, it'll telescope down, and all that will be left is an AR to the n plus 1 minus A. But what I'm trying to find is S. Ellipsis has gone away. I can just divide. Well, can I? Could I? Is there any number that I couldn't divide by? 0. So this is fine as long as r is not what? 1. So at this particular point, we have to say r cannot be 1, because if it was 1, we've got a problem. But we do know this. So the sum of from I equals 0 to n of AR to the I. Nobody pointed that out. I said K up here, had I down there. Keep my indexes the same. Is going to be A times R to the n plus 1 minus 1 over R minus 1 if R is not 1. But what would happen if R was 1? If R was 1, what's 1 to any power? 1. So that's not actually there. So what is this? A plus A plus A plus A plus A. How many A's are there? A plus A plus A is multiplication, it's multiple additions. And so how many A's have been added? Starting at 0, from 0 to 5, right? How many A's are there?
6.
There's 6. So from 0 to n, how many A's are there? N plus 1. So this is A times n plus 1. So that one's handled. So we got that geometric.